Hi everybody. In the last video we talked about direct products, and we showed that if you take a cyclic group of order n and you look at the prime factorization of n, then you can see that Zn is actually isomorphic to the product of cyclic groups of prime power order that you find by looking at the prime factorization of the number n. And in this video, we're going to turn this construction around, and instead of starting with two groups and making a new group, we're going to start with a group, and we're going to look inside it for two subgroups and try to figure out if we can see that our group that we started with is actually the direct product of these two subgroups. And when we can do this, this is called an internal direct product, and it'll give us some information about the structure of our original group. What we're going to do is we're going to first look at direct products and see what their properties are. Then we're going to see if we can find two subgroups which might be the right subgroups to make G their product, and see that in fact with the right conditions that happens. And then we'll look at some examples. So let's start by sort of deducing some general properties of direct products. And the first thing I want to point out is that if you start with a group which is a direct product, let's say of two subgroups H and K, that you can see in the product H cross K, there are two subgroups which are basically copies of H and K. They're isomorphic to H and K. And those two subgroups are, if we let H prime be the collection of pairs where the first component is chosen from H, but the second component is fixed as the identity element in K, and K prime is the collection of pairs where the first component is fixed to be the identity of element of H, and the second component is chosen to be any element in K. And these are subgroups of G. And how do you know that they're subgroups? Well, let's just look quickly at H prime. The identity of the product, which is we know is the combined identities from the two groups. This is an element of H prime because the condition to be in H prime is that the first component is the identity element, second component is the identity element of K, and the first component is any element of H. So this meets that condition. And second of all, we have to show that if we have H EK times H prime inverse EK, and we multiply those together, we get H prime inverse EK using the multiplication rule for the product where you multiply component by component. And this is again in H prime. These are arbitrary elements of H prime. So we've shown that it satisfies the subgroup criterion, and so H prime is a subgroup, and K prime you can make the same argument. And the isomorphism is we define F from H to H prime just by defining F of an element of H to be the pair which has H as its first component and the identity element for K in the second component. And this is bijective because the inverse, if you have an element of H prime, you just take its first component, and that reverses the map. And since it has an inverse, it's bijective. And it's an isomorphism because if you apply F to H1, H2, well, on the one hand, that's H1, H2, EK by the definition of H, but that's the same as H1 EK times H2 EK by the definition of the group law, and that's F of H1, F of H2. And you can do the same with K. So in the product, if you sort of take the groups on one direction or the other, those are subgroups, and they're isomorphic to the groups that you started with. Okay, the second observation to make is that the two factors commute with one another. So that means that what I'm really saying here is that if you take H in H prime, let's call it H prime, and K prime in K prime, then H prime K prime equals K prime H prime for all K prime in K prime and H prime in H prime. And the proof of this comes from the multiplication law in a product. So H prime is of the form H E K, and K prime is of the form E H K. And if you compute H prime K prime, you get H K. And if you compute K prime H prime, you also get H K. So the two factors don't interfere with one another. And this is not saying that H or K are commutative. That's really important. They may not be commutative at all, but their copies of them inside G commute with one another. So the important thing here is that this H is in the first component, this K is in the second component, so that when you multiply them, they don't interfere with one another. And the final observation we can make is that the common intersection, the intersection of these two subgroups, contains only one element, the identity element of H, comma, the identity element of K. Here I've written the identity as 1, 1, but I should have written it as EH, EK. This is the identity in the product. And that's because if you're in H prime, but you're also in K prime, the only way that can happen is that if H is the identity element of H, and vice versa. So these two subgroups, the only element they have in common is the identity element in the group. So an example of this, let me just give you a quick example of when this situation can occur. So let's take Z12. Well, no. We'll get to the example in a minute. So what we're going to prove now is that suppose you have a group, and suppose you have two subgroups which satisfy these three conditions. The only element they have in common is the identity. They commute with one another, and they're subgroups of G, with the property that that every element is every element in G can be written as a product H times K for some H and H and some K and K. That's clear here. Notice that I'm just going to put a little insert here. If you look at G in G, G is equal to HK, which is automatically equal to HEK times EHK. This is in H prime, and this is in K prime. So every element of G is a product of an element in H prime and an element of K prime. If you have, in the general case, you have a group and you have two subgroups, maybe you don't know that it's a product. All you know is that you have two subgroups whose intersection is the identity, which has the property that every element can be written H times K for H chosen from the first subgroup and K chosen from the second, and the subgroups commute with one another. Then it turns out that this group G is actually isomorphic to the product of these two subgroups via the map f of hk equals h times k. And this is called an internal direct product. And for an example, let's skip ahead and look at an example. So we know from our earlier work that Z12 is isomorphic to Z4 cross Z3. That followed from our earlier discussion of direct products. But let's take the subgroups H to be the multiples of 3 and K to be the subgroup which is the multiples of 4. So this group H has 4 elements and it's cyclic, so it's isomorphic to Z4. And this group K has 3 elements, and it's cyclic, so it's isomorphic to Z3. And let's just notice that H intersect K is just 0, and that H and K commute with one another. That's easy in this case because it's a commutative group. They sit inside G, and G is commutative. And the third thing is we can notice is that any element, if I take a congruence class, if A is in Z12, then I claim that A can be written as an element of H plus an element of K. Namely, it's a multiple of 3 plus a multiple of 4. And how do we see this? Well, we can use the fact that 1 is equal to 4 minus 3. And therefore, A is equal to 4 times A plus 3 times minus A for any A. So in particular, let's take 11. 11 is equal to 4 times 11 plus 3 times minus 11. Well, 4 times 11, we view that inside in Z12. This is 44, which is, what is that congruent to mod 12? It's 36 plus 8, so it's congruent to 8 mod 12. And 3 times minus 11 is minus 33, and mod 12, that's congruent to, well, minus 36 is congruent to 0, so it's congruent to 3 mod 12. And so we've shown that 11 is actually is congruent to 8 plus 3, or maybe I should write it as 3 plus 8, and 3 is in H, and 8 is in K. So by a similar trick, you can get every element in Z mod 12 by combining the elements of H and the elements of K. And in fact, that tells you that these two groups satisfy the conditions to be an internal direct product. In other words, G is isomorphic to the product of H cross K, and the map is you send H is 0, 3, 6, 9, and K is 0, 4, 8, and the map is you just add these things together. And that turns out to be a bijective map. And so here we've taken this Z4 cross, we knew already abstractly that Z4 cross Z3 was isomorphic to Z12. Remember how we did that is we showed that the identity element in this group has order 12, and therefore this is a cyclic group of order 12, and we use that to construct an isomorphism. But here we can make that more explicit. We can actually see inside Z12 these two subgroups whose product give the whole group. And in this sense, it's called an internal direct product. Let's therefore go back and see if we can prove this proposition. So the idea is to look at this map, F from H cross K to G, where F of HK is HK, and check, is this an isomorphism? Well, first of all, we need to know, is it bijective? And for that, we need to know, is it onto or surjective? And there the answer is yes by 2. Namely, we know that every G is equal to HK for some H in H and K in K, and therefore every G is going to arise as this combination HK. Is it injective? In other words, could it happen that f of HK, which is HK, equals f of H prime K prime, which is H prime K prime? So if HK equals H prime K prime, then it must be the case that H prime inverse H equals K prime K inverse by moving the K onto this side of the equation and the H onto the other. This is a product of two elements of H, and this is a product of two elements of K, and they're equal to one another. So this element, H prime inverse H, must belong to the intersection of H and K, and by 1, that tells us that H prime inverse H is the identity, or H equals H prime, and similarly, K prime K inverse is the identity in K, so K equals K prime. And that tells you that F is injective. Here we use the fact that the intersection of the two groups is 1, and now we need to use the fact that they commute, and for that we need to check that F of HK H prime K prime, which is F of H prime K prime, which is H prime K prime. On the other hand, F of HK F of H prime K prime is HK H prime K prime. And we want these two things to be equal. And this is where we use the fact that H and K commute with one another. Because of 3, HK H prime K prime is H prime K prime. Because we can move elements of K past H using this property. And so when you put this all together, we see that the map F from H cross K to G is an isomorphism. And so G is, this, in some sense, the same, if you want to think of isomorphism groups meaning that the groups are the same, as the product. And you see how nicely each of the 3 properties come into play. The first one is necessary to show that this function is injective. The second one is used to show that the function is surjective. And the third one is used to show that f of AB is f of A times f of B. So we worked out this example of showing that Z12 is an internal direct subproduct. Now let's look at another example of an internal direct product. So here we're interested in the symmetries of the hexagon. This is the dihedral group with 6 elements. And you remember that it can 12 elements. It has 6 rotations corresponding to the 6 rotations that you can do it to the hexagon. And it has 6 reflections, which sort of come in 2 flavors, the reflections along lines joining 2 vertices, and also the reflections around the midpoints of the edges. And we showed earlier in our discussion of dihedral groups that every dihedral group is given by an element R for the rotation of order 6, in this case because it's a hexagon, S of order 2, which is one of the reflections, you can pick it, with the property that if you do SRS, you get R inverse. And that's because if you reflect the hexagon, so let's say you put this guy over there, and then you rotate to the left one notch. So this vertex here gets reflected to here and then moved by rotation to here, and then you reflect it back. So just to follow through here, we can use just this is a reminder. So this vertex first goes here and then here. So the net effect is this vertex goes from here to here. This vertex, when you do S, is fixed. When you do R, it goes to here. And then when you do S again, it goes to here. So this one goes to here. And since since you know that these are combinations of symmetries of the hexagon, if this vertex goes to here and this vertex goes to here, then you know that basically all the vertices must move one step to the right, which is the same as the opposite of the rotation to the left. So this is just a reminder of how the dihedral group works. We have two subgroups of the dihedral group. One is generated by the identity and the threefold rotation. And that's a subgroup because r cubed times r cubed is the identity. It's r to the sixth. And so this is a little subgroup here of order 2. And now if you take the even powers of the rotation together with the reflections, so you take this collection, this is also a subgroup. And there's various ways to check that. The simplest is to notice that if you multiply even powers of the reflection together, you get an even power of the reflection. Of the rotation. Even powers of the rotation give an even power of the rotation. And because of this rule, if you do S r to the 2i, well, this can be written as S r times r times r, an even number of times S. And another way to read this formula is to read it as SR SS equals R inverse S. And since S times S is the identity, it's a reflection, this could be read as SR is R inverse S, meaning when you move an S past an R, the R turns to R inverse. So this is the same as R inverse times R inverse times R inverse times S, which is the identity. And so this is R to the minus 2i. The important point being that when you multiply a reflection times an even power of a rotation, the result is still an even power of a rotation. And that proves that K is a subgroup. Then we need to check the properties. So it's clear, first of all, that the intersection is the identity. We need to check that every element of G is a product, HK. And for that, all we really need to make sure of is that if we look at an element R to the I S, if I is even, then we're in K. If I is odd, then we can write it as R cubed R to the I minus 3 S, and R cubed is in H, and I minus 3, if I was odd, I minus 3 is even, so this is in K. And finally, we need to check that H and K commute, and for that, we basically need to check that R cubed commutes with these things. And it's clear, I'm going to cheat and move a little down here. It's clear, which is my bad way of saying that I've already done this calculation, R cubed times R to the 2i is R to the 2i times R cubed. So R cubed certainly commutes with the even powers of R. What about the ones that involve S? Well, R cubed times S, and again, I'm going to use this formula here. This is RRRS, and each time the S moves past an R, it turns to its inverse. So this turns into S R to the minus 3. But R has order 6, so R to the minus 3 is the same as R to the 3 because R to the 6th is 1. So this is equal to SR cubed. And that implies that R cubed commutes with all of these elements. For those of you that did the homework problem involving the center of a group, what we've actually proved here is that H is the center of the dihedral group with 12 elements, the dihedral group of the hexagon. So we've checked all three properties, and we conclude that the dihedral group for the hexagon is actually a product of a group of order 2 and a group of order 6. And for the third point here, since H is of order 2, there's only one group of order 2. 2 is a prime number. The only group of order 2 is the cyclic group of order 2. But you can also see this directly. K has 6 elements. And it has a element of order 3, R squared. So it contains the subgroup E R squared R to the 4th, which is cyclic of order 3. And we also have that S R squared S is R to the minus 2. In other words, this is exactly the rule for the dihedral group of the triangle, which we know to be the group S3. So K is isomorphic to D3, the triangle group. So the symmetry group of the hexagon is the product of a group of order 2 and the symmetry group of the triangle. And I invite you to think about what that might mean geometrically. Let's give one example of where something is not an internal direct product. So S3 has 2 subgroups that are interesting. It has the subgroup generated by the 3 cycle, and then it has 3 subgroups of order 2 generated by reflections. So suppose we let H be this and K be E and 1, 2. So here we have 2 subgroups whose intersection is the identity, and which have the property that HK is all of S3. And to see that, you just have to check that when you multiply elements of K times elements of H, what do you get? Well, the only interesting one is when you multiply 1, 2 times each of these 3 elements, and you get 1, 2 times E is 1, 2. 1, 2 times 1, 2, 3 is, so 1 goes to 2 goes to 1. We'll leave 1 alone. 2 goes to 3. 3 goes to 2. 3 goes to 1 goes to 2. And 1, 2, 1, 3, 2 is 1 goes to 3. 3 goes to 2 goes to 1. And so we see that HK together includes these 3 elements, the identity and the 2 rotations, and also contains the 3 transpositions. So G is equal to HK, but S3 is not the internal direct product of these 2 subgroups because they don't commute with one another. The other condition is that 1, 2 times 1, 2, 3, which we just worked out, is 2, 3. If we do it the other way around, here we have 1 goes to 2 goes to 3, and then 3 goes to 1, and these are not equal to one another. So these 2 subgroups meet 2 of the conditions to be an internal direct product, but not all 3, and so S3 can't be split up into a product. So that's the story of internal direct products, and there'll be some homework problems about that.